So we've now looked at how electronegativity can help us determine if a bond is polar or not polar. Ultimately, what we're trying to decide is if a molecule is polar or not. And that comes down to a couple of key things. One is symmetry, so its shape, and one is whether it has bond dipoles or not. Now, being year 13, we are going to assume that all bonds are polar unless the two atoms involved in the bond are the same. So there will be some difference in electronegativity. So therefore there'll be a polarity, a dipole in that bond. We use our trends on our periodic table to determine which would have the higher electronegativity, so have the slightly negative dipole. Basically, we're looking at shape and charge distribution. Bond dipoles affect charge distribution because the electrons get pulled towards a more electronegative element more, which gives asymmetry of charge. There's also a symmetry of shape that can be affected because that creates larger or smaller electron clouds in different parts of the molecule. So I've tried to give a couple of simple examples from last year to start with. I've got the exact electronegativities, thanks Dr. Google, for these elements, so we can see that there are polar bonds here. Now, both of these molecules have got symmetrical shapes. So in 3 dimensions, they're tetrahedral, so they have symmetry of shape. So we can't use shape symmetry to decide if they are polar or not. They also both contain polar bonds. So what we have here is the chlorine has got a higher electronegativity, so in every case the electrons are pulled a little bit closer to the chlorine. But because of the symmetry of shape, those dipoles, the CCl dipoles, all cancel out. So what we have in each of these is a CCl dipole where the electrons are pulled closer to the chlorine than to the carbon. So therefore, we've got these dipoles within the molecule. But because of the symmetry of shape, because all of them are CCl bonds, those dipoles all end up cancelling out. So it's a non-polar molecule. CCl4 is non-polar. Conversely, or oppositely, we've got this molecule here, CCl2F2. So, CF2Cl2, sorry. So, it has got 2 dipoles, and they are different. So, fluorine has got a much higher it's got a much higher electronegativity than chlorine. So the pull it has on the electrons is going to be greater than chlorine. Also look at the differences. The difference between these two is quite large. It's about 1.5, whereas the difference between these two is only about 0.6, 0.7. Okay, so fluorine has got a much stronger pull on those electrons than chlorine does. So even though they both have dipoles that appear to be the same, the effect of the dipole in the CF bond is greater than the effect of the dipole in the CCl. So what we'd end up with is a much stronger pull on this side of the molecule than on this side. Think of it as a tug of war. This side of the molecule wins the tug of war, so it is creating a molecular dipole. So if I was to put a dotted line through here, this side of the molecule would be negative because it's got the stronger dipoles. The CF dipoles have got more effect. And so even though these have got a dipole creating a slight negative on each of these, this side of the molecule is actually going to be delta plus. And again, just reiterating, this is because the fluorines have got a stronger dipole. Sorry, not the fluorines, the CF bonds have got a stronger dipole than the CCl bonds. So it creates that slight negative pole on this side of the molecule. In the next bit, I'm going to go through some of the ones that have got expanded octets to show how that works, because there's some really interesting examples in there. I'm going to use some of the ones are sulfur and fluorine in the next one.